So up until now, we've just been differentiating functions algebraically. You have to be able to show what a derived graph would look like. Now, you actually know more about this than you realise at this point. So, for example, this graph on the left-hand side is currently in the format f of x equals x cubed. Obviously, that's not exactly the formula of this, but it would have an x cubed term in it. Now, if you differentiate x cubed, you end up with 3x squared. So you go from having a cubic function to having a parabola, which is something that you're more familiar with. So essentially what you're doing is dropping one of your turning points each and every time. So going from having this cubic shape, we're now expecting to have a parabola. Now that could either be a maximum turning point or it could be a minimum turning point. Now it's actually quite straightforward to figure out how your graph's going to look. You don't have to do any calculations, you just have to line up turning points and understand the difference between a positive and a negative gradient. So right now this graph has got a turning point here at 0, 0, and it's got a turning point here. Now we don't know the values of that, but it doesn't matter. So this turning point is going to move down and it's going to become a root on our derived graph. So it's staying in the exact same place. This turning point, so turning points move down onto your derived graphs and they become the roots. So turning points become roots. From there, you need to consider the nature of your original graph. So right now, we have a negative gradient going up to our first turning point. Between our two turning points, we then have a positive gradient. After the second turning point, it goes back to having a negative turning point. Now, what the negatives and pluses tell you is the direction that your graph's going in, whether it's lying above or below your x-axis. So if you've got a negative gradient in your original graph, that just means that your line's going to lie below the graph in your derived graph. So it's going to lie down here. So up until the first point up here, it's all negatives. Between our two turning points, it's positive. So that means that we need to join these two turning points together while being above the x-axis. So it would go up and come back down. So it stays above our x-axis. After that, it goes back to being negative. So after our second turning point, or after our root in our derived graph, it goes back down below the x-axis. And that's what our derived graph would look like. So if we repeat that process again over here, so remember your turning points, so we've got this turning point here, we've got this turning point here, and we've got this turning point here. They're going to become the roots on our derived graph. So it doesn't matter the values of them, we just have to make sure we're lining them up on our derived graph. So we've got this point here, this one moves down and becomes a root here, and then this final turning point moves down and becomes a root here. Now keep in mind that we're going from having 3 turning points to suddenly having 2 turning points. So we are now expecting to see 2 turning points in our derived graphs. Every time you differentiate, you drop a turning point essentially. So up until this first turning point, we have a positive gradient. It then goes to a negative gradient between the first 2 turning points, becomes positive again between the second and third, and then it becomes negative at the end after that last turning point. So remember, if it's positive in your original graph, it means it lies above the x-axis in your derived function. If it's negative, it lies below the x-axis. So up until this first root here, it's positive, so it lies above my x-axis. Between these 2 turning points here, it's negative, so I'm going to have to join this root and this root below the x-axis. So it comes down and back up to meet it. Between these 2 turning points, it goes back to being positive, so I need to join this root and this root up above my x-axis. So I'm going to join it up here with a nice smooth curve. And then after that final turning point, it goes back to being negative, so it's staying below my x-axis.